Okay, so it is a problem from section 4.5, problem number 40. Folded boxes. So it says squares with sides of length x are to cut out each corner of the rectangular piece of cardboard measuring 5 feet by 8 feet. So you have this rectangular cardboard, okay, 5 feet by 5 feet by 8 feet. Okay, now what you do here is you cut x feet from each corner and you fold that up to form a rectangular box. So you can try this in your a piece of paper. Okay, so you do that. Now you fold that. Then you fold that. You fold that up. To form.
I have a question.
Sure.
Why are there so many X's at the corners?
Because we have to cut from each corner. You see that? From each corner. We have to cut the square. So we have to cut the square of length x from each corner.
Okay,
Square.
so each of those lines has
length x.
Length X.
Yes, yes. We have to make a square. Okay. So then you fold that up. Now we have to find the volume of that largest box that can be from this way. So then we talk about the volume. Our objective function here is volume. P, right? So what would be that length width times height, correct? That's the volume. Isn't it? Length times width times height. So what would be the dimensions of each side here? What would be the length? What would be the width and height?
Wouldn't length be X?
We cut that out. I wish I can show you in piece of paper. So can you see me holding this piece of paper? Okay, let's say, can you see me or not?
No, we can't.
You cannot?
No, all we see is the notes still.
I can see you.
Right. So there should be ways. If you're using, so let's say this is an 8x5 piece of cardboard. Okay. So what you do? So from each corner, I hope I not. Do I need this? I don't think so. So from each corner, you cut a square out whose length is x by x. Do the same thing on this corner. Okay, from this corner. From this corner. Then you fold that up. You fold that up. to form a box. Open on the top. See that? So then, what would be the length of that box? Originally, we started with a cardboard that has 8 feet length. Anybody? Oh, Gavin, you are right. It's x minus 2x, isn't it? 8 minus 2x, sorry. 8 minus 2x, isn't it? It's early morning. Right? Because we are, so originally it has 8 feet length. Then we cut x unit on one side and x unit on the other side. So now it has length 8 minus 2x. Very good. Very good. What about the width? Similarly, the width will be what? Originally, we started with the 5 feet long cardboard, and we cut x unit from each side. So width will be what? 5 minus, Elizabeth, good. So 5 minus 2x. Now tell me the height. Good. Good. Anybody not understanding this? So the volume is then, V is then, it's in single variable, 8 minus 2x times 5 minus 2x times x. Okay, now what would be, so this is our objective function. Okay, this is our.
Could you help me with something real quick?
Go ahead.
Just how would the height be x? I'm just a little bit confused on that.
Now, if you are now, you cannot see me, right? Can you? So try in your with a piece of paper. So you cut, let's for example, let's say you cut 1 unit from each side, 1 unit, one each side. You fold that up. You have a rectangular piece of paper in front of you. You cut 1 unit. Okay, you cut a square from each corner whose length is 1, and you fold that up. Are you doing that? You have a piece of paper, and you cut a square of length of whose side is 1 from each corner, and you fold that up. So here, look, this is gone. This is gone. Okay, square here. This is gone. This is gone. Now, next step is you. I don't know how to draw this, but okay. Now you fold this. You see that? You fold that up. So your height will be x. If x is 5, your height will be x 5, and so on. Does that help you?
Oh, okay. Yes, I get it now. Thank you.
Good. That's sure?
Yes.
So what will be our interval of interest here? Of course, 0, right? X is the length to what? To, of course, it cannot be negative. So see the highest value of x, that makes the dimension negative. So it is, so here 5 minus 2x has to be positive. If you solve this inequality, oops, negative 5, divide both sides by negative 2. So the largest x can be is 2.5. If you start increasing from 2.5, your dimension starts getting negative. Okay, now we want to find the value of x that maximizes our volume. Understand that? What do we do next? Okay, so this is our volume function. This is our volume function. So either you can just multiply that or FOIL and write in a polynomial form. Otherwise, you can just use the product rule here. Can you find the derivative of this function? Well, let me rewrite this as x times to make this easier for you. Okay, if you multiply by x, you get 8x minus 2x squared. Let's do that so that you have to you don't have to use product rule twice. And the derivative of 8x minus 2x squared is 8 minus 4x times 5 minus 2x plus you keep 8x minus x is 2x squared. Derivative of 5 minus 2x is negative 2. Let's simplify this. You know what? Let's multiply this all together. I think that will be easier for you. That's what I mean. Keep x, FOIL this one. What you get? 8 times 5, 40 minus 8 times negative 2x. It's negative 16x, negative 2x times 5, negative 10x plus 4x squared. It's x times 40 minus then multiply by x here. Do you have any question on this one, guys?
Yeah, actually, I have one.
Sure, go ahead, please.
So in the beginning, where it says interval of interest, and it says 0, comma 2.5.
Right.
How would you know which equation basically to use to get that number?
Look at this length. At minimum, x can be 0, right?
Mhm.
So what is x? You have to go back to here. That is the length of that square you want to cut out from each corner. So this is the length. So at minimum, it can be 0, right?
Mhm.
At maximum, then see this length, width, and height. They cannot be negative. Now look at here. So 5 minus 2x. Okay, 5 minus 2x. If x is, let's say 2, 5 minus 2 times 2 is 4. That is fine. If x is 2, if x is 3, let's say here, 5 minus 2, 5 minus 2 times 3 is negative. That is not correct, right?
Right.
So what do you know? This thing has to be positive. 5 minus 2x has to be positive. And if you solve this inequality for x, you get x is less than or equal to 2.5. So if x is 2.5 here, w equal to 5 minus 2 times 2.5 is 5 minus 5, which is 0. That's fine. But if you start increasing from 2.5, it starts getting negative. Does that help
Okay.
you?
Yeah, thank you.
Good. Now what you do? So we have a volume function. Find the derivative. 40 minus 52x plus 12x squared. Right? Now what you do? You solve this equation for x. You set this equal to 0 and solve for x to find out the critical numbers. So you can use quadratic formula, but we don't have much time, so I would use this Desmo. Okay, what was our equation? Let me write here. 40 minus 52x plus 12x squared, right? So y equals, what do we have? 40 minus, what did we have, guys?
52x.
52x minus, oh, sorry. Oh, this one. 52x
X
plus
12x to the second power.
Oh, okay, good, thank you. Okay, so we have two critical points here. So 1 and 3.33, right? 1 and 3.33. Let's go back. So x equal to 1 and what did I say? 3.33. Okay, so the question is, find the volume of the largest box that can be formed. Okay, so the volume, so what do you do here? The largest volume can occur either at the endpoints or at the critical points. So what do you do? So find the volume at the endpoints. Okay, either at the endpoints or at the critical points. Okay, so if b is 0, if x is 0, so you go back now this factor form is easier. Okay, so b equal to x times 8 minus 2x times 5 minus 2x. Okay, just plug in 0 for x, you get 0. Plug in 2.5x, you get 0. Plug in 1 for x, you get some positive number. Plug in 3.33 for x, you get some positive, and choose the largest one. Understand this? So what did we do here? So first determine the length, width, and height of the rectangle after you cut x units of each square from each corner. Okay, then you have the volume function in terms of x, and determine the endpoints, and then find the critical points and find the volume at the endpoints and also at the critical points. The largest one is your largest volume. Good. Any questions? Any further questions on this one? Okay, then if you don't have any further questions, then we go. Not this one. Mm. 14 point. This should be 6. This one. We're working on this yesterday. Okay, guys. So you know that we are working on yesterday. Oh, am I not sharing my screen with you? I am, right? So linear approximations and approximation differentials. Okay. So what is a linear approximation again? So if you have a smooth curve, if you are able to find, let's say you see the graph on the left hand side, smooth curve, you have, meaning you are able to find the derivative of a function at some point. Okay, just focus on this graph on the left hand side. You have the graph, choose a point P, and then draw a tangent line at that point P, and zoom in, and zoom in, and also zoom in. After successive zoom in, you can see there the graph of the function at that point, near that point, appears to be the tangent line, at that point. So what we do is here, so we approximate the value of the function near that point P using that tangent line. Now we call that linear approximation of the function at the point P. Okay, because we are using the tangent line. So let's say, let's go back here. Okay, so this point is what? Let's call this point P A comma f of A. Okay, and what is the equation of the tangent line passing through that point? Y equal y minus y1 equals m times x minus x1, isn't it? That is the equation of the tangent line. So it is y minus, what is y1 here? F of A equals, what is m? Derivative of the function at that point, times x minus x1 is A. Now if you solve this equation for y, what do you get? Y equals, add f of A to both sides, f of A plus f prime A times x minus A, isn't it? Okay, so this is our, we use the letter L for linear approximation. This is our formula for the approximation of the function near the point P. So this is linear approximation of f at the point A. So this is nothing new. So don't think this is something completely new. So you tell me if you understand the concept here. Do you understand this concept of linear approximation? Hmm? The one condition here is the function has to be differentiable at the point A. Like we also discussed about this yesterday. If the function is not differentiable at A, at some point, let's say at some point Q, like the graph in the right-hand side. Okay, no matter how many times you zoom in, you usually get the same thing. See, you usually get the corner there, at which the function is not differentiable. Okay, so we need to have that condition, linear approximation. Any comment on that? So, well, what does this mean again? Again, this means if you zoom in the graph near the point P, A comma F of A, and if you zoom in successively, the graph appears to be closer and closer to the tangent line at that point P. Okay, so L of x means the approximation, linear approximation of that function at that point P. So we can use this equation. So we get that from equation of tangent line. Sometimes we also call this tangent approximation also called tangent approximation. Okay, good. You're quiet. You're sleeping again? Are you sleeping again?
I have a quick question.
Okay, I like that. Please go ahead.
So, is there any previous notes that you have for this class, like previous chapters? I was struggling a bit more in some of the previous ones. I was wondering if I could get some of those PowerPoint slides, if there was any for those.
For this one, for this time, well, so this is the new section. If you're talking about the linear approximation, this is linear approximation we are using new here. But this equation of the tangent line should be everywhere. So you started from section 2.1, talking about equation of tangent line, haven't you? So y minus y1 equals m times x minus x1. You did that in, it should be everywhere. So you can find that anywhere. So equal to tangent line. So meaning, look, suppose you have a function y equal to 2x squared. Let's say 2x squared minus 5. Now find the equation of the tangent line at the point 2, 3. What do? Y minus y1 equals m times x minus x1. What is y1? 3. What is x1? 2. What is m? That's the thing we do in calculus, right? So this finding the equation, so equation of lines, you did that in calculus, in college algebra or before. But what about the slope here? Okay, how do you find that? Find the derivative, right? 4x, and you plug in what? 2 for x, so it's 4 times 2 is 8. Go back here, y minus y1 is 3 equals 8 times x minus 2, and you solve that for y. That's what you did, right? So
Oh, okay.
the thing we are doing here is nothing different than that. Does that help you?
Yep.
Good. Can you write down this in your notebook so that we can do some problem? You do that?
Yep.
I don't think we can hear you.
Can you hear me now?
Yes.
But it is too much. Oh, I was mute there. You can hear me now. Right?
Yes.
So first find the linear approximation. Okay, so linear approximation, then we can do other things. Lx equal to, what is that? F of a plus f prime a times x minus a, where a is 1 here. Okay, a is 1 here. So what we need here? So what is, let's find it one by one. What is f of a? It is 1. Can you hear me? Anybody?
Yes.
Oh, good. Good. So what you need next? So your function is fx equal to square root of x, which is x to the power 1/2. So what do you want to do? You want to find out f prime at a. So for that, you want to find the derivative. Derivative, which, what is that? You bring x 1/2 to the front, x to the power negative 1/2, which is same as 1/2 is square root of x. Are you okay with that? You bring x to the power negative 1/2 to the bottom, so that becomes 1/x to the power 1/2, which is square root of x. So find out f prime at a, then that is f prime at 1, which is 1/2 times square root of 1, which is 1/2. So we have this we have this, and we have everything we need to find out the linear approximation. Are you with me? Huh?
So we have that f of a equals 1 and f prime of a is 1/2.
1/2, right. So what is the linear approximation of the function at 1? F of a, so you have to go back to this equation. The f of a is 1 plus f prime of a is 1/2 times x minus a is 1. Okay, so this is, if you multiply by 1/2 there, 1/2 x minus 1/2, so it is, what do you get? 1 plus 1 minus 1/2 is positive 1/2, isn't it? Or you can factor out 1/2 and you can just write x plus 1. So that is our linear approximation of the function fx equal to square root of x at the point a equal to 1. Okay, if you draw the graph, so what is the graph of, oh, here. So see the graph of, so this is the graph of square root of x, which is not linear. And this red one is the graph of that linear approximation. The equation of the tangent line, that's the tangent line at the point 1. Okay, so now next question is what? Use it to approximate 1.1. Now use it to approximate square root of 1.1. Okay, so what we learn, so this means what? This means square root of x is close to 1/2. So that is the, so square root of x, that is our original function. Okay, that is our original function, square root of x. So this 1/2 times x plus 1 is the approximation, close enough, very close to that function at the point 1. So how do you find out square root of 1.1 then? Well, you plug in 1.1 for x in the given the linear approximation. Then you can use your calculator to find this number. If I use mine, it should be 1.05. That's what we get when we use linear approximation to find the value of square root of 1.1. Now,
I have a question.
go ahead, please.
So the reason why we're using just 1.1 instead of the square root of 1.1 is because the original function is f of x equals the square root of x. So 1.1 will be x.
Yes, and the other reason is we are using 1.1. Okay. Can you? Well, let me ask this question for everybody. Can you use that linear approximation to approximate square root of 10 or square root of 15 or square root of 5? Can we use this linear approximation to find the value of square root of 10, let's say? Anybody?
Yes.
Well, go back to the linear approximation again. That linear approximation of that function square root of x at which point? At 1. at 1. So when you try to find the square root of 10, that is way off. Okay, so it is at 1. Then you get totally different linear approximation when you find that linear approximation at 10 or 9 or 11. So we are using, to answer your question, we are using linear approximation to find the value of square root of 1.1 because 1.1 is close to 1. Understand that? So we don't want to use that linear approximation to find the value of square root of 10. Okay, so do you understand that?
So if we were to find the square root of 10, we would have to use something closer to 10.
Exactly.
X equals closer to 10.
Yes, maybe we have to find a linear approximation of close to 10 or yeah.
Okay.
But so okay,
Thank
so this is what we get. Just to wrap up this thing. So we get, so this is our approximation of square root of 1.1 when we use that linear approximation. What about if you find out, if you put this in a calculator and find this number, find the exact value? It is, I mean, what do you get if you plug in 1.1 in your function? You should be getting 1.0488. Look, they're very close, aren't they? This is our approximation. This is our exact value. They're very close, right? So I think you'll get some problems when you need to find the error and percent of error. Okay. Now, just to tell you, so what is? No, I think we ran out of time, so we'll just pick up from this tomorrow. Okay. So what is next for you then? Well, I will send these slides to Carlos, and he will upload them for you. Please review them, and that will make our job a little easier tomorrow. Okay. Any last minute question?